Hello, welcome back to this video where we are going to talk more about multiple linear regression. I already motivated the fact that multiple linear regressions are basically necessary when just one independent variable is not really sufficient to explain majority of the variations in a dependent variable. In the previous example, we worked on a data set with two independent variables and one dependent variable, but we worked on these independent variables separately. We built two simple linear regression models, and we saw that one could only explain 39% change in the overhead cost. The other one was able to explain, I believe, 27% of the total variation in the overhead cost. What if you put them together, right? That would constitute multiple linear regression. And in multiple linear regression, the difference between multiple linear regression and linear or simple linear regression is just in multiple linear regression, we do have more than one independent variables. That's really pretty much it. Multiple linear regression equation would look like this. So we do have y as one dependent variable. A is our intercept, b1 times x1. b1 is the coefficient of our first independent variable, b2 is the coefficient of our second independent variable, so on and so forth. And axis here would represent multiple independent variables that we use in our equation. All right, so let's get back to our file. This time I'm working on multiple linear regression.r file. It is already posted on Canvas. Go ahead and download it and make it available to you. And let's open it up. In the last video, I was trying to find the sweeper object here to clean up my console. Actually, I found it. And then if you scroll this pane towards to the right, it will appear here. If you could see it, that's fine. If you hit the sweeper button, it's going to clean up my console. I like it clean. So let's clean my global environment. So let's go back to my home here. So everything looks clean. All right, so we are going to continue working on the Bendix data. So let's get it imported. It's an Excel file. Bendix data is here. Everything looks good. Okay, I don't have to open it up. All right, so let's come over here, load the psych package. Library psych, let's call the structure and describe. We already looked into those, that's fine. In the previous video, we worked on simple linear regression models to explain the overhead costs by using only machine hours and production runs. In this video, we're going to build a multiple linear regression. And the way that you do it is very simple, very similar to the linear regression model. All you do is you represent this tilde as your formula, right? To the left, you do have the dependent variable overhead. To the right, you do have the independent variable. So machine hours plus production runs. So linear model function in R is going to understand that you are trying to fit a multiple linear regression model to explain the changes in the overhead cost by using machine hours and production runs data in your Bendix data frame. And you have to make sure that you are using data equals to Bendix so that R could understand what these column names mean. All right, so we call linear model 4 as our object name. We execute this, and we call summary item 4 to look at the results. So let's carefully take a look at the results, okay? Let me maximize this so that you could see it. Now R understood that I am trying to fit a multiple linear regression model. Let's don't talk about these residuals for now. We're going to talk more about residuals in chapter 11, I believe. So let's focus on this ANOVA table. That's what we call coefficients column. It has this table. This is called ANOVA table. So let's focus on the p-values, not only the intercept. Well, intercepts p-value might violate your 0.05 limit, but we still use intercept. It's most really very important to look at your independent variables p-values. You see that those are very, very small, right? 3 stars indicate that those are nearly 0. Okay, and those are definitely less than 0.05. So that means that both of them are statistically significant in explaining the changes in overhead cost. Well, remember, one of them was just explaining 39% changes of the overhead, and the other one was, I believe, 27%. Right? So what happens if you put them together in the same multiple linear regression? What happens to the R-square value? Well, it jumps from maximum of 39% to 86%. Now, together, machine hours and production runs can explain the change or variations in overhead cost. 86% of the overhead cost. The remaining 14% could be attributed to a different variable or factor other than machine hours or production runs. But 86% is pretty good number. Well, it would be best if we had 100% here, but we don't. The more that we get closer to 100% is better, for sure. That is how you could actually make sense of multiple linear regression. Okay, and what is our equation? Our equation is simply this intercept plus 43 times 536 times machine hours plus 883.618 times production runs. Well, it is already here. How do we make predictions, right? So these are the coefficients that we generated based on this Bendix data, okay? Usually we do train, this is called training. So we train our regression model based on the data that we used as a training, right? We use historical data to train our multiple linear regression model, and we figured out those coefficients. Well, how do we validate it? Well, we validate it by using a validation set, okay? And we do have the validation set stored in a different Excel file. Let's open it up. So we do have Bendix, right? So we already imported it, and I want you to now look at Bendix validation data. And if I open it up to you, you will see that it is exactly the same structure. I do have month information here. I do have machine hours, I do have production runs, and I do have the overhead value. But the only difference is that these are completely different values compared to the training data that I used to train multiple linear regression. If you compare this with the one that I used in R to train my multiple linear regression, you see that those numbers are different. Okay, so now the idea here is that, okay, I use this training data, historical training data, right? I found those coefficients in multiple linear regression. Let's try to see how well those identified coefficients of multiple linear regression on this newly data set available to me, right? Because my regression has not seen these values yet. Can it do better? Can it do still good? Can it do a good job explaining my overhead cost? The answer is we should try, right? So how do we try? We do already have the predict function, right? What we are going to do is we are going to import this validation set first. Well, here's the guideline. So it says that import Bendix validation data and name it Bendix validation. Let's go to import data set. We are importing a data set that our multiple linear regression has not seen before. And it is stored in Bendix validation. Click open. It is highly important that the column names are identical to the column names that we used in the training, right? Because predict function is going to want that. And then we see that we verify that those are the same column names. And then I click import. Okay, Bendix validation data frame is already imported. I go to my multiple linear regression R file. I can just close this. I don't need it. Now, I would like to run the predict function by using the multiple linear regression LM4 that I created here. Right, in this LM4, again, one more time, my dependent variable is overhead, and my independent variables are 2, right? So machine hours and production runs. But I use the Bendix data, the training data. Now I am going to be predicting what's going to happen to overhead cost in the validation data. And this data set was not seen by my LM4 model. And I'm going to collect the overhead values here, and then I'm going to actually call to see what those predicted values are. All right, so let's hit comment and return here first, and then try to see what those prediction values are. So predict function predicted those overhead cost functions for me, and I called them here. These are all 36 predictions that I have. Of course, it is very difficult to see it this way, like how well my multiple linear regression function did. And what I do here is I actually create a validated overhead value in the Bendix validation data frame, and I will store these predictions there. What it will do here is this. So if you go to Bendix validation, it is going to create a new column in my data frame, and it's going to put the predictions here so that I can look at them side by side. Okay, that's what it's going to do. This line 20 and 21. Okay. So Bendix validation is a data frame here. It's going to create a column whose name is validation overhead, right? And it's going to assign the newly generated overhead cost predictions to this column. And I would like to recall this data frame to visualize it. Okay. Now I could see validated overhead versus overhead side by side. Based on linear model 4, the multiple linear regression model that I generated by using the training data, I could actually make predictions on the validation set data, right? You see that those are off, but not really that much, right? So my predictions are off, but not really that much. Can I see it in a different way? Yes, I can plot them for sure, right? I can go ahead and plot this column with this column and in plot function. It is just calling those column names here in line 25. Let's plot them. It is giving me the scatter plot. It looks like, if you had a perfect match, it would be just straight line, right? It's not a straight line for sure, but it's not really that much off. Can I add a trend line here? Yes, I can. By using AB line, right? And calling linear model function one more time. And in this linear model function, I am literally doing a simple linear regression, but you don't really need to worry about it too much. Just call this line 27 to add a straight line here, right? If your predictions were like 100% with 100% are 100% accurate, you would have seen all these dots on this simple trend line. It's not, but those are not that much off from this trend line, right? So actually, we can say that my multiple linear regression is doing a good job explaining the changes of the overhead that it has never seen in the validation set data. So in a nutshell, this video touched based on what a training data set is, what the validation data set is, how we can train a certain model, and then how we can implement it on a different data set that the model has not ever seen before. By this way, we would validate the accuracy or the prediction power of the model that we can generate. We are going to talk more about these concepts as we move forward with these techniques in the future. On the next video, we are going to take a look at how we can actually to identify categorical variables in multiple regressions.